Hello everyone, I am Surendra, Master Teacher in Vedantu. I have brought a series for KVPY preparation for SA stream, and our today's topic is PNC. Although PNC is one big chapter, I have taken one very important topic for today's session, that is distribution of objects, distribution of distinct objects, and also distribution of alike objects. And in this I will be talking about two important concepts. One is group formation and one is beggar coin method. We will also see if constraints are given, how to deal with them. Okay, so first please understand, when we have to distribute n distinct objects, we have to distribute n distinct objects among m persons, and let us call these objects to be O1, O2 and so on, On. So because we have to distribute the objects, so every object will have m options to go. So m ways to distribute first object, and same will be for second object, and similarly same will be for the last object. So if we use fundamental principle of multiplication and we multiply these m, I think it will be n times. Okay, so this becomes m raised to the power n. So please remember this as a formula. I have seen student getting confused between m raised to the power n or n raised to the power m. Please remember, we have to distribute the objects, not otherwise. So this is correct, this is wrong. There is one more thing here, that here there is no restriction that which object will go to which person, or at least one object should go to one person. Here we have taken all possibilities. Maybe all objects may have gone to one person. So if any restriction is to be applied, then we have to use some other thing that is known as group formation. What is this group formation? Please understand. Suppose we are having m plus n objects. I am talking about this first point. We are having m plus n objects, and we want that m objects to go to one person, okay, and n objects to go to the other person. M objects, n objects. So what we will do, we will first divide these objects into two groups of size m and n, okay, and then we will distribute these two new objects. I'm calling first group, one of the group as object 1 and this group as object 2. So these objects we will be distributing to these persons. So if both persons to get one object each, I think here number of ways will be 2 into 1. For first object we will have two choice. For second object we will be having only one object, one option. So after creating these two new objects O1 and O2, and then if we multiply by 2 into 1, we will be able to distribute these objects. So this is the idea behind distributing the objects such that m goes to one person, n goes to other person. So here first thing is that how to distribute them into two groups. One of them is having m objects, other is having n objects. So there is a direct formula. Please remember this result. It is m plus n factorial upon m factorial n factorial. It is actually coming from this m plus n c m. Okay, because we have to just choose m objects, other group will be created automatically. So from here it is coming. So please understand, this group formation or formation of group is like creating new objects and without any preference or order. Why I am saying so? Please understand. Suppose we were having two balls. The question was very simple. One is red ball, one is green ball. And we have to distribute these two balls into two persons, so each get one ball. Okay. So once we have created these two groups here, or we are having two balls, red and green, after that there is no difference if we have to distribute them among two persons. I hope you are getting my point. What I am saying, this formula will be only creating two new objects without any preference, like red ball, green ball, whom you can distribute later with whatever condition you are given or whatever way you want to do. Okay, so here for second one, which is just example of this, so it will be 15 factorial upon 10 factorial 5 factorial. Similarly here it will be 15 factorial upon 3 factorial 5 factorial 7 factorial, and this again will create 15 objects into 3 new objects. One of them will have 3 old objects, second will have 5 old objects, and third will have 7 old objects. And these 3 new objects are without any preference order. You cannot call this is first, this is second, this is third. We are just creating these 3 objects, and now whatever way you want to distribute them, you can do. Okay, now why I am emphasizing on this thing without any preference, I have to tell you one more important thing here, that suppose if your objects, if your groups are such that 2 of them are having same size. So in this case, our earlier formula was m plus 2n whole factorial upon m factorial n factorial n factorial. This will not be sufficient. Please understand why. Suppose we are having m plus 2n objects here, and we have to distribute them into m, n and n size groups. So because this formula will be able to give you all possibilities in which any m objects will be here, any other n objects will be here, and any other n objects will be here. So there will be chances that whatever objects were put here, they might go to this place, and these objects might go to this place. So in this formula, we will be actually repeating, we will be counting them as different, that objects going into this, then these objects going to this another group, and similarly the objects or the content of this last group coming to the second group. Okay, so this way there will be repetition. So what we are going to do, we will be dividing additionally by 2 factorial so that we do not get any repetition. Let me repeat once again. The purpose of formation of groups is to create new objects without any preference order. So whether your same n numbers comes to this place or they comes to this place, it doesn't matter. Okay, so to avoid this duplicacy or this repetition, we have to divide by 2 factorial. Okay, so this is one additional thing that we have to take care of, and then whatever you have to do, you can do later. Okay, I'll tell you this through examples also. In this case, 12 objects are to be distributed into 3, 3 and 6. So here what will be the answer? 12 factorial upon 3 factorial, 3 factorial and 6 factorial, and additional 1 upon 2 factorial, because 2 groups are having size of 3, 3 each. Similarly, for this 6th case, if we take, I think it will give you more clarity, 12 factorial upon 1, 2, 3 times 2 factorial. So let me write in one go, and 2 times 3 factorial, so 3 factorial square. But the additional division has to be done by 2, 2, 2. So 2 group of size 2 are 3, so there will be 3 factorial. This 3 factorial is because of this, and into 2 factorial, and this is because of this. Okay, so this will be the result if we have to create these 5 groups of size 2, 2, 2, 3, 3 from 12 different objects. Okay, so this will give you 5 new objects. Now you can decide what you want to do for these objects depending upon what is given in the question. Okay, so let us take one very simple question on this thing. We are given in a jeep, there are 3 seats in front and 3 in the back. Number of different ways in which 6 persons of different height can be seated so that everyone in front is shorter than the person behind him. Okay, they are saying that suppose this is my front row and this is my back row. So the person here, okay, should have, let me call this as person I and let me call this person J. So the height of PI should be shorter than height of person J. Similarly, you can say this as PA, this as PB. We can call this as PC, this as PD. So what we have to do, we have to make sure that height of PA is greater than PB, height of PC is greater than PD. So what I am going to do here, I will create three groups. I will create three groups of 6 persons. So I will create three groups of size 2 each. So it will be done in how many ways? 6 factorial upon 2 factorial, 2 factorial, 2 factorial, and additional division by 3 factorial. Okay, and this will give me the possible three groups. Okay, and this, if you calculate, I think it comes out to be 720 upon 8, and I think here it will be 6. So this becomes 15. So 15 ways are to create three groups of 2 persons each. Now there are two things you need to take care of, that every group will have 2 persons of different heights. So the person with shorter height will go into the front row, and person with bigger height will go to the back row. But also we can arrange them into these 3 columns, you can say. Any one of the group can come to column 1, column 2, or column 3. So my final answer should be 15 factorial into 15 into 3 factorial. I hope you are getting my point. So this will become I think 90. So that is the answer. Okay, so I hope you have understood how group formation has been helpful here, that we first created the groups so that they can be then fitted into these 3 columns, first, second, third, and then every column you will be able to fit each group exactly one way, because person with shorter height will come in the front seat and the longer height will come into the back seat. So this way answer will be 90. Although I can give you one more way, I will not say better way, but one different way for doing this question. Please understand how. Suppose we are arranging all the persons in these 6 seats. So it will be done in 6 factorial ways. Okay. Now let us focus only on the column 1. In this 6 factorial ways, in column 1, we may have person with bigger height in front row, or maybe otherwise also. So can I say that half of this 6 factorial ways, there will be exactly half cases will be when person with smaller height will be in the front row, and half will be the cases when smaller height person will be in the back row. So I have to take only the half of that. Now after doing that, same for column 2, half cases out of this will be when person with smaller height will be in the front row, and half of these cases will be when person with smaller height will be in the back row. So I will be again doing 1 by 2 so that I get only those cases in which person with smaller height is sitting in the front row. Similarly, after doing this means till this point we have made sure that person with smaller height is sitting in front row of column 1 and column 2. If we want this for column 3 also, so we have to divide 1 by 2 once again. So this will also give you the answer as 90 only. So this can be done in 2 ways. So that completes the answer of this question. Coming to the next question, please see. This question says n belongs to n factorial. We have to prove that n square factorial upon n factorial into n factorial power n plus 1 is an integer. Okay, so n square means you can write this as n square. N square factorial means you can write this as n factorial into n square minus 1 and so on up to 2 into 1. So these are n square integers, you can see, and I think we can write them as n square into n square minus 1 and so on, n square minus n plus 1. So this is my first group of n objects. Okay, this is the first group of n numbers actually, and then n square minus n, then n square minus n minus 1 and so on, then n square minus 2n plus 1. So this will be another group of n numbers. I am sure you will understand because there are total n square numbers. So we will be able to break them into n such groups of n objects. If you remember, we do such question in which we prove that any n consecutive numbers are divisible by n factorial. So this will be divisible by n factorial, yes or no? This will also be divisible by n factorial, and similarly this will also be divisible by n factorial. But what we have to prove? We have to prove that this is divisible by n factorial power n plus 1. If you notice here, this way if we go, then we only have proved that this is divisible by n factorial power n. This n square factorial is divisible by n factorial power n, not n plus 1. Okay, I hope you are getting what I'm trying to tell you. So how we can tell that there will be additional n factorial factor if we divide n square factorial by this n factorial n times. So please understand what we will do. We will use the group formation theory. Assume there are n square objects, okay, and we want to break them into n groups, each of them having n objects. So if you remember, I told you the formula, it will be n square factorial upon this n factorial size. N factorial will come because of each group size, so it will come n times. But because there will be additional n factorial, because all the groups are of same size, so this will be the number of ways. This will be number of ways to create n groups of n objects each. And as you know, we can definitely do this thing. You can understand easily, like you are having suppose n square objects. You have to put first n at one place, then next n at other place, and so on. So this has to be an integer, yes or no? So this has to be an integer. So if this has to be integer, that is only possible if n square factorial is divisible by n factorial power n plus 1. I think this is done. Let me write it here. So this n factorial whole raised to the power n plus 1 divides n square factorial. That's it. So this can be a very good use of group formation in in number system question also. Although let me tell you, this question can be done by number system also, in which you can find additional n factorial factor, but here I am talking about only group formation. So this is how this is done. Now coming to next question, and let me tell you, this question is from previous year JEE Advanced. I think 2020 this was asked. You are given that in a hotel 4 rooms are available and 6 persons are to be accommodated in these 4 rooms in such a way that each of these rooms contains at least 1 person and at most 2 persons. Okay, so I think it is very easy to see that if 6 persons are to be accommodated, so that each of these rooms contain at least 1 person, so 4 persons will be accommodated this way, but additional 2 persons can be accommodated only if you give 2 persons to any 2 of the rooms and one person each to other 2 rooms. So I think what we have to do, we have to first create 6 persons. We have to create groups of 6 persons into 4 of size 2, 2 and 1, 1. 2, 2 and 1, 1. And this group formation will be done in how many ways? 6 factorial upon 2 factorial 2 times, 1 factorial be 2 times, and then I have to divide additionally by 2 factorial 2 factorial. But till this point of time I have only created 4 objects. You can understand 4 objects, and they are, you can say, O1, O2, O3, O4, and these O1, O2, O3, O4 has to be given to 4 rooms. So every room gets 1 object, isn't it? So there we have to multiply by 4 factorial. Please understand, there is a restriction. Every object or every group of either 2 person or 1 person has to go to exactly 1 room. So 4 factorial will be multiplied here. So we can see it will become 6 factorial is 720, and here we are having I think 16, and into 4 factorial is 24. So this 8 2 is 16, 8 3 is 24. Let me divide this also by 360, yes, and 360 into 3 will be 1080. So the answer for this simple question is C, and you can see this question was asked in JAIN Advanced. Now coming to distribution of alike objects, also known as beggar coin method. What is beggar coin method? Please understand. Here we are distributing n identical objects and read this as coin or coins, okay, among R persons, and then call these R persons as R beggars, okay. And if I am having n coins and I have to distribute them among R beggars, beggar cannot force you to give one of them or two of them as maybe at least 3 coin or at least 4 coin. It is all up to you whom you want to give and whom you do not want to give. So that is how beggar coin is one very appropriate name. One more thing, suppose you are having all 1 rupees coin. So all of them are identical. Which coin will go to which beggar, it doesn't make any difference. If you give 2 coins to this beggar, 2 coins to the other beggar, then which 2 coin is going to this or which 2 coin is going to the other, it will not make any difference. We are assuming all coins are of same denomination. Let us say 1 rupees. So here, if we have to distribute n identical objects or coins among R persons or R beggars, so that each person may receive any number of objects, then this is the formula: n plus R minus 1 CR minus 1. You can also write this as n plus R minus 1 Cn. Okay, there is one very easy proof for this. I will not go into detail of it, but I'll just give you the hint. Suppose you are having n coins, so put them into a row like this, n coins. Now if there are R beggars, then put R minus 1 vertical lines in between, R minus 1 vertical lines in between. Okay, now wherever these lines go, the first portion will go to beggar 1, the second portion will go to beggar 2, this will go to beggar number 1, this will go to beggar number 2, and so on. Okay, so wherever your lines will go, you will be able to distribute your n coins among R beggars accordingly. So here you can see the question is reduced to just arrange R minus 1 identical vertical lines and n identical coins. So this will be n plus R minus 1 factorial upon n factorial R minus 1 factorial. So that's it. Now this formula is very, very important. It is very useful in many places. I will try to show you in 2-3 examples. So let us start with this one. Very easy example. Please see. We have to find the number of integrals of integral solutions of x plus y plus z less than or equal to 16. And x is greater than or equal to 2, y is greater than or equal to 1, and z is greater than or equal to 0. Okay. So please understand, in this question, what is happening, you can make analogy to beggar coin method. Please see how. Suppose you have 16 coins. Okay. So you have to give some coins to beggar number 1. Let us say x number of coins going to beggar 1, then y number of coins going to beggar number 2, and z number of coins going to beggar number 3. And this sum is less than or equal to 16, which means you are not forced to give all the coins to these 3 beggars. But in this formula, if you remember, I told you all coins will be given to these beggars. That is how we created, we got this formula. Okay, so here I think this formula will not be applicable. So what we can do, please understand, you can keep these remaining coins with you, okay, or you can imagine there is a 4th beggar. So whatever I will be left with, I will give this to the fourth beggar. So can we say that this question is equivalent to x plus y plus z plus w is equal to 16, in which w will be greater than or equal to 0. So we have actually assumed, or we have actually imagined to have fourth beggar. So whatever will be left out, it will go to the fourth beggar. You can think of yourself also as the fourth beggar if you are keeping it into your pocket. So this is what this less than or equal to sign, this is how it will be replaced by this equal to sign. But here one more thing, please understand. We are given the instruction that x should be greater than or equal to 2, means our first beggar should be given at least 2 coins. Similarly, second beggar should be given at least 1 coin. So in this case also, we are not in this situation where this formula is applied, n plus r minus 1, c r minus 1. So what we will do, we will first think of that, let us give 2 coins to beggar number 1 and give 1 more coin to beggar number 2, and let us define new variables like x0 and y0, z0 and w0. And because I have already given 2 coin to beggar 1 and 1 coin to beggar 2, so we will be now left with 13 coin here. But now I think we are in the condition where we are not forced to to be given any coin to any beggar. All these x0, y0, z0, w0 are greater than or equal to 0. So here this is a perfect condition for beggar coin method. Hence we can apply the formula. Number of coins are 13. Okay, number of beggars are 4 minus 1, c 4 minus 1. So here the answer will be 13 plus 3, 16, c 3. That will be the answer. Okay, so this is how you can do this question, and I have actually taken this question with many variety of conditions taken into one question, like less than or equal to I have taken, x greater than or equal to I have taken. So I have tried to include many things here, but there is one more thing that is to be taken care of, and that I will take into this question. Please see what this is. This question says, in how many ways can a dice be thrown thrice by a person to make a sum of 12? So you are throwing a dice. Let us say first dice you throw, you get x. Second dice you throw, you get y. Third time you throw the dice, you get z. And the question says you need to get this as 12. Okay, here the condition is, please understand, that x, y, z, they all will be greater than or equal to 1. Okay, if that was the only condition, then it was okay. We have done in our previous question, but that is not the only challenge. I think there is an upper limit also, that they all should be less than or equal to 6 also. I hope you are getting my point. Suppose if I only think of this greater than or equal to 1 at a time, then I think this will become x0 plus y0 plus z0 is equal to 9. You can think of these are 3 beggars. Each of them we have to give at least 1 coin. So we have given them 1 coin. So I am now left with 9 coins. And now number of solutions of this equation, or it is like distributing 9 coins among the 3 beggars. So answer here will be 9 plus 2, 9 plus 3 minus 1, C3 minus 1. So it will be 9 plus 2, I think 11, C2. We can find answer also. I think it will be 9 into 5, 55. 11 into 5, that is 55. Yeah. But as you know, this is not the answer. Why it is not the answer? Because if we have taken x0, y0, z0 this way, I think our condition on x0, y0, z0 will be greater than 0, but they will be less than or equal to 5 also. So those solutions in which x0 takes value 6, 7, 8 or 9, we don't have to accept them as a solution, because my x0 has to be less than or equal to 5. Then what is to be done? Please understand. We will be subtracting those cases in which x0 is greater than or equal to 6. Please listen carefully. This 55 is the solution only if my x0, y0 and z0, all three are greater than or equal to 0. But to take care of this upper limit, I will subtract those cases in which x0 becomes greater than or equal to 6. Okay, so let us assume that my conditions are that x0 is greater than or equal to 6. Now y0 and z0 are again on the same condition, greater than or equal to 0. Okay, so this was our original equation. This was my second equation. Now, because x0 has to be given at least 6 coins, you can think of that way, then the second equation can be written as x0 dash plus y0 plus z0 is equal to, I think here we can write as 3, because we have to give at least 6 coins to this first beggar. I am talking about that case in which x0 becomes greater than or equal to 6. So here this will be this way, x0 dash plus y0 plus z0 equal to 3. So to solve this again we can use the beggar coin. So how much will it be? 3 plus 2, 5, C2. If you use that formula directly, it gives you 10. I think if x0 can be greater than or equal to 6, y0 and z0 can also be greater than or equal to 6. Isn't it? Similarly, this y0 and z0 also greater than or equal to 6 will give you 10 and 10 each. So we have to subtract 10 plus 10 plus 10, 30 cases from this 25 to get the answer. But here, please understand one more thing, that if x0 becomes greater than or equal to 6, I think number in equation number 2 is so that y0 or z0, they separately now cannot become greater than 6. So only the condition of x0 greater than or equal to 6 is sufficient. We don't have to check for that both x0 greater than or equal to 6 and y0 greater than or equal to 6. It is not possible, so we don't have to take care of this. So the answer here would be 55, okay, minus this 10 3 times. So answer here should be equal to 25. Okay. I would like to add one more method to this question. We are given that in how many ways sum can be 12. So this was actually x plus y plus z is equal to 12. Okay. Can we write x to be equal to 6 minus x1, y is equal to 6 minus y1 and z is equal to 6 minus z1? Why I am saying so? If that is so, then our equation will become, please see, x1 plus y1 plus z1 is equal to 6. And also because these each of x, y and z were from 1 to 6 both included, so this x1 will be from x1 will be from, I think it can take 0, it can take 1, 2, 3, 4 and 5. So x1 can take these 6 values starting with 0, 1, 2, 3, 4, 5. So you can see all of them. It is not only for x1, it will be for y1 also and z1 also. So here you can see x1, y1 and z1 will be greater than or equal to 0, but it will be less than or equal to 5. So if I use beggar coin method here, you can see we will get answer 6 plus 3 minus 1, 3c minus 1, which comes out to be 8c2, which is 28. Here what we have to subtract, we have to subtract only that case in which x1 becomes equal to 6. You can see because their sum is 6 and x1 is less than or equal to 5, so there will be only one case when x1 will be equal to 6. Okay, one case. Similarly, one case when y1 will be equal to 6 and one case when z1 will be equal to 6. So we have to subtract these 3 cases from this 28 and you can check we are getting the same answer from this method also. Now coming to this question which says let n be the number of functions f 1, 2, 3, 20, let us call this as a, to the same set A satisfying fi greater than or equal to fj for 1 less than or equal to I less than j less than or equal to 20, then we have to find n. So first of all, let us understand this thing here, that as we increase I to j, the value of function at j is lesser than or equal to f of I, which means it will be either decreasing or it will be constant. So better to call this kind of function as non-increasing. Okay, now to understand what exactly be going on in this question, please understand, let this set be A here and this also as A here, and 1, 2, 3, 4 and so on up to 20, and here 1, 2, 3 and so on, let me call this as 7 and so on, then 20. I am taking just one example. As you all understand, if this is a function, every element of A has to be connected, but every element of this domain A has to be connected, but not of this codomain A. So if our range is, please understand, if range is 1, 2, 3, 7, just 4 elements in the range, okay, then please understand, because it is non-increasing function, okay, so this smallest element of domain has to be connected with 7, yes or no, if range is 1, 2, 3, 7. In fact, this 20 will also be connected with 1 because it is non-increasing. So first element will get the highest possible value, the last element will get the least possible value, and in between you can put accordingly in many possible manners. Like if we have to connect 2, so we can connect 2 with 7 also, or we can connect 2 with a smaller element also, and smaller than 7 is 3 here. So for 2, after this connection, we have two choices. Either 2 can be connected with 7 or 2 can be connected with 3. So suppose if it is connected with 7. Then for 3, again we will be having two choices. Either it will be connected with 7 or it will be connected with smaller element, that will be 3. We cannot connect 3 with 2 because if it is connected, then this element 3 will be missed and it will not be there in the range. And similarly, for 4, now we will be having two choices. Either it can be connected with 3 or it can be connected with 2. So suppose if it is connected with 3, then for next element again, same way, for every element we will be having two choices. One, that it is connected with what its previous element was connected, or it is connected with one lesser element. But once this 5, suppose is connected with 2, okay, and let us assume 6 is connected with 1, then between 6 and 20, every element has to be connected with 1 only. This is the meaning of this question. I have not discussed how we will be solving it. I have just told you that what is the meaning of this question. Okay, now please understand what will be the method to solve this question. Suppose the range of this function is some set which will be definitely subset of this set A. Okay, so we can assume that whatever elements are there in the range, they will be connected with one or multiple element of domain A, and which are not there in the range, they will be not connected with any element in the A. I am calling, let us call elements of codomain A as beggars, okay, and elements of domain A as coin. Okay, and if we use the beggar coin method, I think answer is direct. So this distribution can be done in 20 plus 20 minus 1 C 20 minus 1, that is 39 C 19 ways. Now this was the method. These number of ways are to distribute 20 coins to 20 beggars. Now there are possibilities that some of the beggar will get, some of the beggar will not get. Let us assume that beggar 1, beggar 2 and so on, all beggar up to beggar 20. This beggar 2 got, let us say, 3 coins. Beggar 7 got, let us say, 4 elements. Beggar 9 got, let us say, 5 elements. Let me add them. 3 plus 4, 7. 7 plus 5, 12. And let me give all remaining to this 20. Okay, so 3 element to beggar 2. 2 means Here it will be element 2 in this codomain. Here this will be element 7. Here this element will be 9, and here this element will be 20. Okay, now please listen carefully. Isn't that mean this element 2 of codomain will be connected with exactly 3 elements of this domain? Similarly, element 7 will be connected with exactly 4 elements of this domain, and so on. But because it's a non-decreasing, non-increasing function, so can we say that first 8 element means 1 to 8 will be connected to this 20 number element? Please understand, because it's the non-decreasing, non-increasing function. So these 8 element cannot be anything other than first 8. Okay, so if this B20 or this 20th element is connected to 8 elements of this domain set, then these 8 element has to be 1 to 8. If they are not, and they are from some other elements like 10 or 12, then this condition will not be satisfied. Please think it yourself. Okay, and then these 5 elements for this element number 9, they has to be 9 to 13, 9, 10, 11, 12, 13. Yes, 5 elements. Okay, similarly these 4 element has to be 14 to I think 17, and these 3 element has to be 18 to 20. Okay, so what I am trying to tell you here, that once we have found that in how many ways elements, the 20 elements of this first set or domain set A can be distributed to 20 elements of codomain set A, I think after this we have only one way to connect them, isn't it? So this n has to be, 39C19 only. So that is the answer. I hope you have understood how easy it was. If you understand that just beggar coin method was sufficient to solve this question. Okay, so this is how this can be done. Let us move to the next question, which says from first 80 natural numbers, 5 numbers are chosen so that no 2 of them are consecutive. If in how many ways this can be done? Okay, we have to find in how many ways this can be done. So I have 2-3 methods. Let us discuss them one by one. First method is that we are having 1, 2, 3 and so on up to 80. And let us assume the chosen numbers are n1, okay, n2, n3, n4 and n5. I think 5 numbers we have to choose. So these are the 5 numbers that we have to choose. Now, because no 2 are consecutive, so you have to have some numbers in between n1 and n2. Let us call that as x2. Why I am saying x2? Because there can be some elements before n1 also. Although it is not mandatory, but you may have also, because they are not saying that you have to choose one. Okay. Similarly, in between here, you have to choose, let us say, x3 number of elements or x3 number of numbers. Similarly, x4 numbers here, x5 numbers here, and x6 numbers here. So I am sure it is very easy to understand that x1 plus x2 plus x3 plus x4 plus x5 plus x6 will become equal to 75, isn't it? Because 5 numbers are taken away, so this will become 75. But here x1, x6 can be greater than or equal to 0, because it is not mandatory to leave any element on these corners. But for these x2, x3, x4 and x5, the values has to be greater than or equal to 1. Okay, so exactly similar to what we have done our previous questions, we can, call these 6 beggars, call these 6 variables as beggars, and we have to give at least 1 coins to these four beggars each. So our new equation can be written as x1 plus x2 dash plus x3 dash plus x4 dash plus x5 dash plus x6 is equal to, I think, 71. We have given 1 coins to each of these 4 beggars, so that we are in that condition that now we are not constrained or we are not forced to give any one of the coin or more coin to some given beggar. So here I think this equation will be solved exactly by the beggar coin method, and there are 6 number of beggars, so answer will be 71 plus 6 minus 1, so I think 76C5 is the answer. Okay, so that is one method. Let me give you one more method for this question. Please understand carefully. This is actually gap method. This I call as the gap method. And to understand it better, I will just take one analogy. Please understand. Suppose we are having 80 chairs, okay, in which 5 are red and remaining 75 are white. Okay, and we will arrange these 80 chairs in a row in such a way that no two red are consecutive. Okay, so arrange these 80 chairs so that no two red are consecutive. If that is so, consecutive, okay, if that is so, then what we will do, we will write the number 1, 2, 3, 4, 5 up to 80 from one end to the another, and whatever number will be written on these red chairs, we will take those numbers away. And because no two red chairs are consecutive, so those numbers which are taken, they will not be consecutive. I hope you are getting my point. So in such questions, what we do, we first arrange white chairs. Okay, so first is arrange white chairs, and that will be done in one way only, because all the white chairs are identical. Arrange 75 white chairs, W means white chairs, in one way, and then between these 75 chairs, okay, and sideways there will be total 77 gaps. There will be total, 76 gaps. Between and sideways there will be total 76 gaps, and so out of these 76 gaps we have to find 5 gaps. So find 5 gaps out of 76, and that will be done in 76 C5, and in the last arrange those 5 red chairs at 5 gaps. Okay, this will again be done in one way only, and then use the multiplication principle. So 1 into 76 C5 into 1. So this is how it can be done. I hope this is clear. Okay, I have one more method. Let me just tell you orally, not that big method. Let me tell you, if you have to arrange 80 chairs such that no two red are consecutive, so what we will do, we will take 4 white chairs away. Okay, then we will be having 5 red and 71 white. 5 red, 71 white, and then arrange them in whatever way you want to do. It will be 76 C5. Okay, but if you do this way, there are chances that maybe 2 red chairs may come together, or maybe 3 red chairs come together. Then those 4 white chairs which we took away, now put 1 each between the gaps of red chairs, because 5 red chairs if are put, you will find 4 gaps in between. So 1 each white chairs to be put in between these gaps to make sure that no two red chair is consecutive now. So that way also you can do it. So 76 C5 will be the answer, whatever way you want to do it. Okay, so that is the answer for this question. Now coming to this question, this question is also the continuation of our previous question, in which we are given that 80 natural numbers are written on a circle and 5 numbers are chosen so that no two of them are consecutive. So question is saying that on a circle 1, 2, 3 and so on, and 80 will be here. 80 natural numbers are written on a circle in that order. Let me write this also in that order. And 5 are to be chosen so that no two of them are consecutive. So this is also, similar to our previous question only, But the problem here is that now 80 and 1 are consecutive. So you cannot choose 80 and 1 together. Okay, so suppose these numbers were written on a row 1, 2, 3 and so on and 80. Okay, so we found that in our previous method the answer was 76C5. So what is that we also need to take care of is that R1 and 80 they cannot be selected together. So I think if we take care of that, I think our answer we can get the answer. So out of the 76C5 we just have to subtract in which 1 and 80 both are selected. Okay, if they both are selected, what will happen? Actually 2 will not be selected and 79 will also not be selected if we go by that rule that no two consecutive numbers are selected. I am talking about those cases which are counted in 76C5 and 1 and 80 are also selected. Okay, so in that cases, out of these only, if 1 and 80 are selected, 2 and 79 will not be selected. So we have to select only, so we have to select now, so 3 numbers to be selected from, I think 76 numbers. And these 2 so that no 2 are consecutive. No, so that no 2 are consecutive. So if we have understood our previous method, you can do it now faster. 76 means you will be first placing 73 white chairs, and for that we will be having 74 gaps and we will choose 3. So 74C3 will be the number of ways for this. So here the answer would be, here 76C5 minus 74C3. So this is my one method. Okay, let me tell you there are 2 more methods. What are 2 more methods? Please see the method 2 here, and then method 3 also I'll discuss. Method 2 is that if we do not want to do this way, okay, or maybe we do not want to use that earlier method, then the earlier result, then what we can do, we can make cases. Number 1, that 1 is selected, okay, or 2, 1 is not selected. Okay, if 1 is selected, I think you all understand 2 will not be selected and 80 will also not be selected. Okay, so again I think this will be similar question to our previous one, only 4 to be selected, or only 4 from 77 to be selected with the same condition that no 2 are consecutive. And if you understand my previous methods, so here you will be having 73 white chairs, so 74 gaps, C4 for this one. If 1 is not selected, then we are free to choose 2 also, we are free to choose 80 also, but in this case only 5, in this case 5 from 79 to be selected, isn't it? With the same condition that no 2 are consecutive. So once again 79 minus 5, 74 white chairs, so 75 gaps, and 75C5 will be answer for this one. So if you add them, 74C4 plus 75C5, you will get exactly same as this also. It can be checked, they both becomes same. You can convert them into each other also. So that is my second method. There is one more method that is also very, very interesting method, let me tell you. Yeah. So that, what is that method? Please see. First of all, 1, 2, 3 and so on up to 80, 79 and so on, somewhere 20 here, 30 here and so on like this. So let us assume that we are selecting first element from any one of these 80. So this can be done in 80C1 ways. And let us assume we selected 3. You can select any one of them. Now, once this 3 is selected, you cannot select 4, you cannot select 2. And after that, we still have to select 4 more elements from 77. So this is similar to this first case of method 2. So the answer will be 74C4. This will be for, for those 4 elements, for those 4 more elements after 3 selected. Okay, because 77 and we have to select from 74 from 77. So there will be 73 plus 1, 74. Yeah, exactly. This will be the answer. But now please understand, whatever 5 elements we have selected, we could have started with any one of them in this 80C1 ways, isn't it? Because when I'm saying 80C1, then this can be 1 also, this can be 2 also, this can be 3 also, and so on. For example, if in this example which I have taken, my first element was 3, then I selected 20, then I selected, let us say, 30, then we selected, let us say, 79, and we selected 1. Okay, so you can see these 5 elements are selected, but in this 80C1 when we are doing, we could have started with 1 also, and we could have ended up with selecting these 5 elements only. After 1 we can select 3, 20, 30 and 79. Similarly, we could have started with 79 in this 80C1, and then also we could have selected 1, 3, 20 and 30. So you can see this selection of 5 elements will be actually repeated exactly 5 times. So we have to divide it by 5. So if you do that, you will get 16 into 74C4. So this is also the answer for this question. So you can check, we are getting 3 different expressions. One was 76C5 minus 74C3. Yeah. And the other one was 74C4 plus 75C5. And the third one is 16 into 74C4, and it can be checked. They all gives you the same answer. Okay, so this is how this question can be solved. One very important question, and I like this question very much. That's why I've taken in this session. Now I'll be now telling you the teaser question, but before that, let me tell you KVPY sessions are there on YouTube channel VOS, where you can find sessions every Sunday at these timings for KVPY SA as well as SX stream. Dear all, if you are preparing for JEE Advanced or you want to prepare in future, then Vedantu Eklavya is one big thing in online domain. You must know about it. If you are not already aware, please do the Google. You just Google it, you will come to know. I'm here sharing few links with you. This is the link for notice board, where we are putting all important informations about new batches coming up or any new things going on in these batches. So please follow this notice board to know about new things going on here. And this is the QR code for the same thing. You can go to the same thing from these 2 routes, and these things are shared in the description box also. If you are writing JEE Advanced this year 2022, then this is the link and QR code for a Telegram channel. So just join it. We will be putting all relevant information there so that you can join appropriately. Similarly, for 2023 aspirants, for 2024 aspirants, these are the links and QR code, and join them, and you will be made part of those. Channels, and we will be giving you relevant information there. We also created a YouTube channel with the name IPAT, where you will find the solutions of JEE Advanced and KVPY. We have recorded solutions question wise, and we have tried to give best possible solutions, and in fact sometimes 2 methods, 3 methods. So please watch these solutions there whenever you need. Okay. Now this is the teaser question. Everybody please see. The question says, consider the cube whose vertices are 8 points x, y, z, for which each of x, y and z is either 0 or 1. Number of ways are there to color its vertices black or white such that any vertex, if all of its neighbors are of same color, then it is also that color. Okay, 2 vertices are neighbors if the 2 end points of same edge of the cube. Okay, Two neighbors only if two endpoints of the same edge of the cube. So you have to find, actually, let me write it here. You have to find number of ways in which we can color its vertices black or white, so that for any vertex, if all the neighbors are of the same color, then it is also of the same color. One of the possible way can be that all of them be black or all of them be white. But that is just one thing. Please figure out what all possibilities are there. Okay. Thank you so much, everybody. I'll be waiting for the solution for this teaser question. Yeah, one more important thing. The solution of this teaser question should come to this email ID with this subject line, teaser solution maths. We will be waiting for your solution, and if we find your solution to be good, we will ask you to come with us. We will be interacting with you, and wherever we find appropriate, we will make you part with us. Okay. So that is all for today. Thank you so much. Bye everyone. Take care.